Alright, so we are discussing in the middle of module 3. We already have started with the modern block ciphers, and to just recap on what we were doing, we were mostly focusing on areas of block ciphers and stream ciphers. In that also I told you that most of the time what we are going to focus on will be based on the modern block ciphers. And the basic reason why we are choosing that, because in terms of stream cipher, the problem is that it's one bit at a time, and it is instead of block cipher where we have more number of combinations that is possible in terms of the plain text as well as in terms of the key. Especially given the fact that if we have a longer number of bits for the key, there will be more possible ways of substitution that will take place, and that was given by some kind of a expression which was given in terms of logarithmic values. It was given like this. And I told you that in terms of if the keys are used in terms of transposition, then the key length will be defined by log to the base 2 n factorial long. Whereas with respect to substitution, it will be log to the base 2, but it will be 2 to the power n factorial long, which makes it even more difficult for the cryptanalysis or any brute force attack, or for that matter to decipher. So keeping that in mind, let us move ahead that how we can generate these keys in different ways. But for that, we are leading towards data encryption algorithm, which is or data encryption standard, which we call as DES. But in terms of DES, to know DES, we need certain tools. Okay, we need certain tools to understand the process of DES. DES is actually the basic first of the standard encryption technique which was introduced, although it had certain drawbacks for which the AES comes in to picture. Okay, so we'll first discuss DES, but for DES we require certain tools, and today's class is dealt with all those tools and principles. But they are very interesting, so hopefully you will be able to reconnect to this whole process. So the first thing that comes up for our discussion, why there is a noise at the please. So you can observe that modern block ciphers normally are keyed substitution cipher. By that keyed substitution cipher, what I mean is, you can see the second line, and that's a very important line in fact, that in most of the cases you will soon find that we are going to use certain permutation or combination for that matter. It's not that the normal, in the terms of mathematics, we are not talking about. It is just the different set of arrangement that we are talking about. And in that arrangement, if that arrangement is predefined, before even you are making the encryption happen, if the predefined combinations is presented to us, then we are mostly, we'll look into that as a keyed generation or the keyed element as such. So you can see the second line in which the key allows only partial mapping from the possible inputs to the possible outputs. Whereas modern block ciphers, we are going to use certain blocks which are called as P-boxes, S-boxes. So this P-boxes, S-boxes, and what are them? Because all these boxes will be used later on as sum. P stands for permutation box. You can see the next line itself. P stands for permutation box. So P-box parallels the traditional transposition ciphers to characters. And since we are not dealing with characters now, we have already established that we are dealing with bits for that matter. So it transposes bits as well. And the process is that it is a keyless, which means that the mappings are predefined. So please make a note of this single word. If it is a keyless element, wherever you will find keyless, it means that the mapping has been predefined. Now, what is mapping? I will let you know after this. So, most of the block ciphers, the techniques that you are coming up across, you will find that the mapping will be predefined. It is not that dynamically the combinations will go on changing. Okay, so that's a predefined mapping that we are going to follow. So, what exactly are this mapping? So, let's see this with a very simple example and a diagram which will give us an understanding of this P-box. Now, if you observe closely, there are three types of P-boxes which are present or mostly being used. In the first one, that is called as straight P-box, which is given over here. Alright, the next one is called as compression P-box, and the next one is called as expansion P-box. Now, as from the diagram, it is very intuitive and very clearly you can understand the purpose of the P-box. Now, if you observe the first one, which is a straight P-box, in that we have 5 such inputs over here, 1, 2, 3, 4, 5. and there are 5 such output which are 5, 1, 2, 3, 4, 5. Now in between, there must be some kind of a mapping between the input and output which are given by these red connectors. Now this is why we are calling this as a keyless, because this is a predefined structure for that particular algorithm, how you are trying to make it up. Now it is not that always 1 and 4 will be connected or 2 and 1 will be connected. What does this mean? That if 1 comes in as the input, output will be 4. Okay, so basically if the input is 1, 2, 3, 4, 5 in this sequence, then ideally you are supposed to get as 4 when we have 2. No, 2 is given by 1, and then we have 3 as 5, 4 as 3, and 5 as 5. So, sorry, 5 as 2, sorry. So this is how the process is. Now, why it is called straight? Because this is a straight relationship that we are existing. Now, it doesn't mean that this is the only possible combination that is there. You can have different set of links and accordingly it will be generated. But naturally, you can imagine where it will be used mostly when the input and the output bits you want to keep it same. Alright, suppose you have a key which is of having 16 bit, for example, and the output will also be a 16 bit for that matter. Okay? And naturally, you can imagine the combination of this nature will be relatively easier amongst all the three to break in such manner. Because this is all the possible. Suppose the key length is small, then you actually can possibly see what are the possible combination it can have. And you can decipher that easily. So this is what the principle says about the straight P. Now, we'll come to the details of it after this slide. Now, next one, if you observe, this is called as compression P box. And very clearly you can see that why it is called as compression. Because input you have 5 bits over here, whereas the output you have 3 bits. So basically you are giving an input of 5 bits and you are getting a 3 bit. That means in some algorithm somewhere, if you are implementing a compression P box, then suppose you have a 64 bit of data and you want to shrink it to something like a 56 bit or maybe less than that, then maybe a compression P box suits the requirement. And another advantage on how we are implementing that, if you observe very carefully, again, simply you can see it, that although inputs are there in each of the nodes, 2 and 4 is not connected by any chance. So that makes it eventually that 1 is mapped to 1, 3 is mapped to 2, and 5 is mapped to 3. So although there are 5 inputs, but there are 2 inputs which are not being addressed at all. And that's how we are making the compressed P box. Alright. Remember, these are the elements to the DES algorithm. We are going to use them at certain point, but this is one of the very important segment of our discussion. The next one, in fact, is directly used in DES, and that is called as an expansion box. It's just the reverse of it, but you can observe that how it is done. There are multiple connections over here. Although there are 3 bits as input, but you are getting 5 bits as an output. So basically, somewhere during the processing, you have synced the data to 48 bits. And now suppose you want to get back the original data. That is where you are going to use an expansion box where the reconversion will take place. From 48 bits, suppose an expansion to 64 bit. So those additional 12 or 16 bits that you are going to connect to, that may be done using an expansion box, given that there are some mapping which exists between the bits. Now, if you observe here, 1 is connected to 1 and 4, so multiple connection. 2 is connected to 5, 1 connection. 3 is connected to 2 and 3. So there are multiple connections that are possible. And again, naturally, these are all one of these snippets of the combination. There can be n possible such process that is involved, right? So this particular P box plays an important role in generating the combination or generating the different set of bits. When you consider those 1, 2, 3 or those 1, 2, 3, 4, 5, these are digital data, ones and zeros. So we can observe that how many possible informations or how many possible changes we can make to the data. Keeping in mind that this all is a part of encryption technique, so it will improve the security aspect as well. right? So this is about the three basic blocks. Now let's see about what exactly are these in detail. So if you observe, this is one of the example already I took it. So a straight P box has n inputs and n outputs. And if you observe here that there are 3 bits as an input we are giving. So these are the possible combinations that we can have, and we can have these are the possible outcomes that you are looking at, all possible combinations together. So that's basically what the straight P box is doing. Alright, this already I have explained it to you, so I don't think we'll need much time in that. Now when we have n equals to 64, okay, when we have n equals to 64, suppose the number of bits are more. So in that case, what is happening, if you observe that this is one of the possible mapping which is usually used, and it will be very helpful later on as well in your DES. That's why this example is there in almost all the textbooks and all. Now, if you observe here what exactly is happening, the entries, if you observe that they are all within the bound of 64, okay, all they are bounds. You can see 64 somewhere here, and you can see 0 somewhere, 0, 1 is here. Alright, so all the possible combinations are there. Now, how this is made? This is using some kind of a P box where there are 64 inputs and they are interconnected somewhere in between, such that what does this 58 indicate? You can see what is mentioned over here. Table has 64 entries because n equal to 64, corresponding to 64 inputs. Now, what is the significance of the table? The position of the entry corresponds to the output. That means the first entry contains number 58, 58 over here. What does that mean? The first output comes from the 58th input. So basically, internally, 1 and 58 is connected somehow. We cannot draw that box to show all those 64 steps. So this table is indicating a possible combination. So if for the first output that comes in, so this is my first output. But through which input it will come? 58 input will produce the first output. Similarly, the last one, if you observe here, last one. So that will be called as the 64th output will come through the 7th input. Can you understand what exactly is meaning? We are making sure that there are a combination which is placed, a particular permutation. It's not that this is the only one of the combination. There can be any other arrangement as well. And in that arrangement, however with the arrangement, the meaning of it is that the first output will come through the 58th input. So 1, 2, 3, 4 like that. When the 58th input will come in, that will generate the 50, that will be the first output. Similarly, suppose for any example you take, for example, the 10th one here. So it will be like 1, 2, 3, 4, 5, 6, 7. So the 7th output will be through 10th input. 7th output will be through 10th input. That means 7 and 10 somewhere is connected. Understood? So that is how one of the permutation table will be there for any of these encryption algorithms, especially DES, as we are going to discuss that in further in future. So most of the time what will happen, there will be a predefined table. That is why they are called as keyed element, because of this mapping is already predefined, predetermined. Right? So based on that, this table is formed, and accordingly, whenever the input or the output is generated, we will remap once again, trace back to which input it is supposed to get connected to. Clear with this idea? How the mapping is done? That's one of the example, because this is the standard one given in textbook, and most of the illustration it will be there. Now, keeping that in mind, this is another example of that same logic. So, design an 8x8 permutation table for a straight P box that moves the two middle bits 4 and 5 in the input word to the two ends, that is 1 and 8. Now, this is a certain logic, certain rule that has been imposed on a straight P box. As I said, there is no certain rule to it. It's just that we want to make the combination happen. So in this case, what is happening? You can observe that out of 8 bits, so 1, 2, 3, the 4 and 5 has been appended somewhere over here as per the rule. So that means the fourth output, you can see the first output is mapped to the fourth input. And the last 8th output will be mapped to the fifth one. Suppose this is the logic for a particular arrangement. Now, based on that, you are going to design the system and you will understand that the output when you are generating, if it is 1, if you are getting an input, so if you are getting the first output, it will be mapped to the fourth input. So you can see fourth input. If you are mapping the the second output, it will be mapped to first output, first input here. Same way, third output will be mapped to second input, like that, and so on and so forth. Right? So the mapping is very important. The combination of the permutation table, we call this, is very important in scrambling the data, if you call it that way. Understood? It's not that we are going to send 1, 2, 3, 4, 5, 6, 7, 8. We are just scrambling. This is a small little example in that 4 and 5 has been shuffled, or the middle bits have been taken care and it has been shuffled, and that makes a whole lot of change in the encryption process itself. Clear? So this is one of the small example, but the way we are going to read the table, that remains the same. In the previous example, if you go back, the same thing we read. The first output is nothing. The 58, the first output will be mapped to 58 input. The same way you can see the fourth output, the first output will be the fourth input. So it will be mapped to the fourth input, like that. Now fourth input can be like 1, 0 bit pattern, something will come in. So based on that, it will be calculated. Okay. So this is about the first part. Then comes again another example. You can see that if this is a compression box. This is where the compression box happens. So that means we are compressing it with respect to what the input is. So you can see compression box, we have n inputs and m outputs. Naturally, in the diagram already I showed you that if there were 5 inputs, we are getting only 3 outputs. So the same thing is condition is given over here. M is less than n. So the output is less than the input. And if you observe in this particular table, this is being given as a table 32 cross 24 permutation table. And if you observe here, these all are blocked. Now you can ask me, sir, why these are blocked? The answer is I don't know why they are blocked, because there can be any other design you can make in which you may have block 10, 12, 15, 17, 19, so on and so forth. You can do that. Alright. So the process is that the logic behind it, that whenever we require to swing the data, we are going to use the compression table. When we are going to expand it, we will require the expansion P-box. So here, if you observe, the same kind of table is mapped over here. So in this case, although as it is not a straight connector, you can see, observe over here, that the first output is mapped to first, the second output is mapped to second input, third in that way. But when you are going to fourth output, it is mapped to 21st input. Got it? So the reading is the same way we are going to read the statement. So the fourth output is basically the 21st input. Same way we are going to map the other things. Now, this is another example. This is expansion. In fact, this is the expansion example. Here, if you see, the opposite thing is happening. M greater than N. So in this case, 12 cross 16 permutation table we have. In that, you can see that there can be scenarios where there are multiple connectivity that is happening. Some of the inputs are connected to more than one input. The expansion P-box used in modern block ciphers normally are keyless. That means this is predetermined rule is there. Now that rule is set by the programmer or the algorithm whoever is using it. Based on that algorithm, you can map it accordingly. Note that each of the input 1, 3, 9 and 12 is mapped to 2 inputs. 1, 9, 12 and 3. If you observe, they are appearing multiple times. So basically, that's how we are doing it. Okay? So that's basically the expansion box for us. Expansion P-boxes are used when we need to permute bits and increase the number of bits which are required. You will soon find the importance of this statement. It's very, very important at times to make these changes happen, because it's not always possible to arrange that much of memory space to allocate that many number of bits. So that's why we can shrink it in a smaller dimension. Alright. So that's why we are actually using this. Right. Now this is again another very important property that comes in with P-box, and that is called as invertibility. Now what does that mean is that whenever we are using this kind of a P-box, it's always advisable that whether the decipher we are doing the encryption at the transmitter end. Or when you're deciphering at the end, whether at the receiver, we can use the opposite technique, opposite method to get back the data. Now in that, the compression and the expansion box, remember, they are not non-invertible. That means the receiver will have to have a separate mapping in order to decipher the data back. But in case of straight box, it is possible for the receiver to get back the data only by rearranging the data sections, just as given over here. So you can see a straight P box is invertible, but compression and expansion boxes are not. We will soon find why they are not. We'll use another example. So you can see the original table has, suppose it is a P box, some example. So 1, 2, 3, 4, 5 and 6 are arranged in this order. Now, if we add the indices, like how they are being mapped, and if we rearrange and sort accordingly, you will see that the final result also has the same set of elements as that of the initial element. Maybe a rearranged one, but the elements are the same. Because we remember that this is where we are using m equals to n. The input and the outputs are the same. So whatever happens, the combination wise, most of the time the elements will be within the set of elements which we started off with. So the combination will remain as it is. Right? So that's why it is an invertible option that we can have. Unlike two, the next two, which is given over here. Now see this example. Input 2 is lost here. When the input was there, when the input came in, let's suppose this is the transmitter and the second bit is blocked. So we got some output as 2. Now suppose at the receiver, I have sent this 2 bit. Now we are expecting that this 2 bit will be mapped to 3 bits. That's basically the invertibility we are talking about. But as you can see, output 2 cannot be assigned to a definitive value, because the receiver might not know that whether this connectivity, this 1 is connected to 2 or 1 is connected to 3 or 3 is connected to 1 or 2 is at all getting blocked like that. Because compression happens in a one directional way. It's only a single direction that it is going on. So the opposite end, it doesn't work. Similarly in expansion box, you can see the resultant over here. Transmitter is fine. But when you are looking at the receiver end, output of the 1 and 2, this 2, cannot be selected definitely. It might work, but it might not also work. Because you never know what are the multiple connections it might have come across while it was generated. So in a way, the bottom line is a straight P box will be easy to decipher, because the combination at the transmitter and the receiver will almost be identical, if not different combination only, like different patterns of the same bits. But in case of compression and expansion box, it is much more difficult to decipher what was there in the input. So naturally, the utility of this compression and the expansion box will be much more in our explanation after a certain period rather than the straight P box. Straight P box is like more like a easy way out. Same number of bits coming in, same number of bits going out with certain combination. But here what is happening, even if you know the data, you are not sure how the transmitted data was or how the initial combination was there. I'm talking about the intruders here. The receiver definitely will know. The receiver in the sense like they will have the key, the pattern and all. But I'm talking about the intruders who are trying to get your data. They might not be able to decipher it from the information that they might have. Okay, because of this multiple connection in expansion box or the multiple connection or no connection or disconnection on the compression box. So that's why these two are very largely used rather than the straight P box. Alright. So that's about the P box, which happens to be a very important element to our discussion for DES, leading towards DES. Any doubt in that P box and all? Anyone? This is a permutation box. We will have a permutation table. That table is not a standard table. There can be n possible ways of making that table. But whatever happens, we have to understand that the output and the input should have some kind of a mapping. It can be 1-to-1. It can be more than 1-to-1. It can be scrambled somehow. Right? So that is the basic physical significance of this P box. Right? Next, what we have is we call as the S box or the substitution box. Please make a note of this substitution box. It will be helpful directly. We will use in our DES algorithm. So this is S-box have different number of inputs and outputs. All right. And it has a very important role because in this is more like a generic approach in which we are going to use it mostly for the compression of the data or the data rearrangement. So the input, in other words, the input to an S-box could be an n-bit word, but the output can be an n-bit word where m and n are not necessarily the same. So it doesn't mean that it should be a straight P-box like m equals to n or m greater than n or m less than n. So based on our availability, S-box will vary. We can arrange accordingly. Same or it can be different. So that's why S-box you can say it's a generic box to that of P-box. Whatever we have done in P-box, it's an additional part to it. Alright, it's a generic approach towards it. That's why we will find that for DES as well as for AES, we are going to use S-box. We are going to use the S-box rather than P-box. Because P-box is specific, expansion, compression, straight P-box. But in case of S-box, we can use it according to our need. Alright, so that's the advantage. So S-box can be keyed or keyless. Naturally, if it is keyed, it means that there is a certain permutation or a certain combination of bits or the input-output relationship will exist. And keyless is, it can be dynamic as well. So that's the advantage. So it can be keyed or keyless. Modern block ciphers usually use keyless S-boxes where mapping from one input are predetermined. Remember, keyless means mapping is predetermined. Okay, and keyed means it can be dynamic. Alright, please leave the meeting. Alright, so that's how the whole thing. Now, how it works. Alright, how the mapping is done. S-box, this is not required as much, but it will be leading to certain answers. So it's very easy actually. You can see, observe here. So suppose there are inputs x1, x2, x3 up to xn. Okay. And you have the outputs which are y1, y2 up to ym. So there are n and m number of inputs and outputs present. Now the relationship between the input output can be represented in terms of a function. That's the main catch here, function. This function will play an even more important role rather than anything what you are discussing over here. This function will have an important role. Why? Because all this modification of the existing data set will be done with respect to this function and how you are defining the function. You will soon find, if time permits, we are going to discuss about the Fiestal cipher today itself, because that is also a building block to DES. That actually works with respect to this function. Okay, so we'll see that one by one. So what is y1? Y1 is a function of the input. Y is a function of, you can see y1 is function of x1, x2, x3 up to xn. Again, y2 is a function of f2, but again the same number of bits are coming, x1, x2, x3 up to xn. And after we are getting all this, how we are doing it in general? So the linear X box can be represented in the form y1 to ym with a matrix formation like this: a11 x1 XOR a12 x2 up to a1n xn, like that. Or in general, basically you are trying to make a matrix multiplication happen for a linear S box. Okay, so let's see about a linear X box. Let's see about this is one of the snippets or the important information over here. So the linear S box is given over here, where the y and the x is having a linear relationship and there is no such product term exists over there. Product term means there is no such x1, x2 or x2, x3 or x3, x4 like that. No product term is available over here. That's why we are calling this as a linear S box. And in our discussion, whatever we are coming across, most of the time we are going to face a linear S box only. And you can see the non-linear S box has no such relationship for the output is possible. So a linear S box, what the role is, so if you go back a little while back when we were trying to discuss about the combination or the permutation box, P box, the basic logic was the input and the output should be mapped. Now we are discussing in a way where the analytical skills comes in, where we are introducing some kind of a function that relates the output to input. Now, if that relationship is a linear relationship, we are calling that as a linear S box. If not, then we are calling it as a non-linear S box. And non-linear means there will be combination. I will give you an example after this. Maybe an x cube factor or an x1, x2, x3, where x1, x2, x3 are the inputs to the box. So let's see one by one. So suppose this is one of the, yeah, please. So if we have this as an example, if you observe, so we have y1 given by x1s or x2 plus x3. Now in this case, a1 and a2, if you observe, so the statement is linear X box with 3 input and 2 output. 3 input, 2 output. So is it not very similar to that of the compression P box that we considered? Number of inputs are more than that of number of outputs. So it's basically similar to the compression P box, but we are dealing with a more generic, more dynamic box or a black box, if you say, which will go on changing its configuration as per our requirement. So in this case, there are 3 inputs and 2 outputs, and it is represented as y1. Outputs are y1 and y2. And the generic equations are given by a linear relationship x1, x2, x3 with XOR operation. And the second one is only having an x1. That means A2 and A1, like the coefficients of the second one is having 0. So you can see that this is given by over here, and we can represent it in terms of a metric representation as well. So it's more easier approach in which we actually can arrange the input and output and the relationship exists between them, and we can map it. Because remember, this is also a part of the mapping that we are doing. Right? So this is about the linear S box and how it works, although we won't be investing much into this part a lot as of now. Let's take with 2 inputs, 3 inputs and 2 output, but here the equations are supposed like this. Now this is a non-linear example, non-linear S box, because you can see there are x cubes over here, there is an x square over here, there is an x1, x2 over here. So this is a non-linear S box which cannot be represented. You can see there is no linear relationship between the input and the output in that manner. But as I said, we most of the time will be focusing on linear S box, so we don't need to worry much about this part itself. So S box is a process in which the substitution is happening, but with certain degrees of mapping between input and output. That's all what we need to know. Now, along with that, this is another example how the S box is working, just like we had a P box example. Please concentrate on this a bit. This is one of the possible mapping that we are trying to do. How we are doing it? See, the following table defines the input-output. See, defines the input-output relationship. That means this is specific to a requirement. Based on your requirement, you can change it accordingly. So, what is the relationship? What is the conditions given? The leftmost bit of the input defines the row, and the 2 rightmost bits will be defining the input column. So now if you observe, there are 3 bits. So the possible combination that we can have is, I have written it down in the right hand side. Now in that, the left hand side bit, that means this part will be rows. Okay, so we are defining this as row. The first bit, so 3 bits at a time 3 bits will come. So the first bit is for the row. The rest 2 bits will be considered over here. That's why you can see 0, 0, 0. This is one of the combination. 0 is over here in the left hand side, and the 00 has come over here. And this, along with this, you can see the output bits have been given certain numbers. Now this is based on certain relationship that exists between y1 and x1. Some relationships are there, but we are not bothered with that because we are more bothered with the table. Why we are bothered with the table? Because if you observe carefully, the logic behind S box is, suppose the input is 0, 0, 0. Input is 0, 0, 0. How many outputs do we have? 2. 3 input, 2 output. So what we are observing, 0, 0, 0. So we move this way. 0, 0, 0. If the input is, the output will be 0, 0. Suppose the input is 0, 1, 0. 0, 1, 0. Input is 0, 1, 0. Wherever it will intersect, 0, 1. So 0, 1 will be corresponding number. So my question is, you can see here, it's given over here, that if the input is 0, 1, 0, 0, 1, 0 is over here, the output will be 0, 1. When it is 1, 0, 1, 1, 0, 1, the output will be 0, 0. Now there are, as I said, this is a mapping predefined based on certain rules as and when required, and we get this table. So now we are in, suppose this table is there, we have made the S box with this table inbuilt, So what we are going to do, we are giving the 3 input bits 0, 0, 0, 0, 1, like that it will go on one by one. Accordingly, the output will have a logic in which the data will come in accordingly. Right? So that's basically the role of an S box. With respect to a predefined structure, it is going on generating the outputs randomly, which are not there, like 0, 0, 0, why it is 0, 0, or for example, why it should be 0, 1. This is done by some kind of a linear relationship that exists between y1 and x1, which we have defined. It can be like 2 x1s or 3 x2 plus 3 x3, maybe. Okay, maybe that may be a relationship based on which the table has been formed. Now, whenever the input comes in, it will be like this, nature. So this S box is a mapping tool. To give you another example, where we have more than 3 bits, let's take this as an example, and please make a note of this little bit, like the keywords, because this 64 bit, if you observe, you can see this is a table of 6 cross 4. It's very important because we will soon find that this will play a role in DES as well. Now, what we are looking at, that 6 input and 4 output. So there is basically some kind of a compression is happening over here as well. 6 inputs we are including, 4 outputs we are getting. Now the logic behind this is that the outer 2 bits for any 6 digits, for example, here is given as 0, 0, 1, 1, 0, 0. So the outer 2 digit will be considered as the row, and the middle portion will be considered as the x-axis. Right? So that is how the output is looking at over here. So if you see, the 4 middle bits have been mentioned over here. So the logic behind this is, suppose the input is 0, 0, 1, 1, 0, 0, like this. So where does it end? So first of all, we have to exclude the first and the last bit. So 0, 0, where is 0, 0? It's over here. So 0, 0 lies somewhere here. Now what are the middle bits? 0, 1, 1, 0. Where is 0, 1, 1, 0? 0, 1, 1, 0 is here. So wherever it will intersect, 1, 0, 1, 1. 1, 0, 1, 1 will be the output. Right? In the previous example, when we had 3 bits, we were taking the first bit as the row and the rest 2 as the column. Same thing almost we are doing, but here the extreme 2 bits out of the 6 bits, we are considering that as the row. So 2 bits is gone in the left hand side, if you see the 2 bits over here, and the rest 4 bits are arranged in such a manner, one after the another based on the possible outcomes. It's there in the x-axis, like in the column wise we are looking at. So similarly, you can see 0, 0, 1, 1, 1. So 0, 1 exists over here, 0 and 1, and middle bits are 0, 1, 1, 1, 0, 1, 1. Where is 0, 1, 1? 0, 1, 1 is here. So we go like this. We go like this. So the output is 0, 0, 1. Now, as I said, this is one of the mapping. This is one of the mapping. For example, suppose you have chosen the first 2 letters as the row and the rest 4 as the column. Maybe one of the combination. Understood? So that's the flexibility that a S box gives us in making different set of combinations, and based on different set of rules, we can define the 4 bits at a time. Now, suppose you have multiple such S boxes. Now you have like 8, 10 S boxes, which are generating this many number of 4-digit number, which are fairly random in nature. So then you can imagine those keywords are, if they are used as a key, then how much randomness you are generating in the key, so that to make sure that a decipher will not be happening that easily from any interface. So basically this part of the study is based on the mapping and to scramble the data as much as possible. Alright, so this is about the S box example. Let me finish off with 2 other examples. So this is again one of the example in which the S box relationship is existing over here. So it is invertible. You can see the S box, the relationship between input and outputs are defined by a table of mathematical expression, which we have defined, a linear relationship that we have. They may or may not be invertible. If they have to be invertible, then the number of input bits and the number of output bits should be same. So M should be equal to N, and then only it is possible to have that invertibility. For example, you can see here, it's a 3 cross 3 element. And in the same manner, the example that we took, and this is the table. This is the table used where the left hand row is considered, left hand bit is considered as a row, and the rest of the 2 bits are considered as a column. So this is the input table used for encryption, and the 3 bits are given over here. In the decipher, in the receiver end, you also have the similar kind of element where you are observing that the 0, suppose you take anything. For example, if the input to the left box is 001, the output is 101, 001. So this is what we are looking at. 001, the output is 101. Now in the input 101 for the right table, 101, you are getting back that 001 once again. So if it is M equals to N, then the same table, the input, the transmitter and the receiver end will have the similar kind of pattern so that the invertibility is maintained. Okay, but if M and N is not equal, which in most of the cases will be, it is not possible. You will find in DS, it will be that 6 cross 4 that I showed you. In that case, it is not possible to come back from the other end to find out what was the input bit.